Hey everybody, and welcome to a sort of teach as you go video where we are going to go over a technique that I've kind of made up as my own technique for graphing polynomials. This isn't exactly how it's necessarily taught by books. I'm not really a big fan of how graphing polynomials is taught in most textbooks and most places. I'm quite annoyed by how it's taught in a lot of places, and it's crucial that you become quite decent at graphing polynomials for a few reasons. For one thing, in pre-calculus you'll use graphing polynomials, this concept, underlying concept, to do inequalities with polynomials and rationals. You'll also, from there in calculus, if you go on to calculus, you'll use this underlying concept for the first and second derivative test quite a bit. And the way it's taught in books and the way it's done in most places, it's with testing intervals, and it's just inefficient, it's slow, there's a lot of risk for inaccuracy. It's just, I'm not a fan, and I feel like we can do better. We can do a lot better, and it's quite ridiculous that it's not widespread taught the way I'm going to show you today. So let's kind of get into this. This example is going to be the most basic type, which I'm not a fan of, but it is the one you'll see probably most typically, especially in an Algebra 2 course. The next example, which I'll have a thumbnail pop up at the end of this video, the next example will have two other things going on in it, which I think is a little bit better for kind of showing you the scenarios that can occur when it comes to x-intercepts. So less talking, let's get into it. Let me show you what to do. So here we are given a polynomial equation. It's already in standard form. It doesn't need to be in standard form, but you have to remember that if it's not in standard form, if it's in factored form, when you're doing the first step that I'm going to list off, you got to be careful because people screw up. So I have a little mnemonic device. I made it up. It's not perfect. It may change in the future. And what is that, you ask? Well, it's a bunch of letters, a little sentence, and the first letter in each word of the sentence translates to the first letter in the step, if that makes sense. So we're going to have exotic, funky, zebras, avoid, little, purple, grapes. So hopefully you wrote that down and you repeated the little sentence for yourself so you know what I intended it to stand for. The kind of the weirder it is, the little easier it is for you to remember. So exotic, funky, zebras, avoid, little, purple, grapes. Exotic, the E, actually is representative of end behavior. If you're here doing this right now, you should have already had a lesson in class on how to determine the end behavior of a polynomial. This is not the time where I'm going to be going over that. I don't remember if I have a whole entire video on that. If I do, I'll try to link it at the end or below. If not, I'll try to make one and link it at the end or below. F stands for everyone's favorite thing, factor. Z is not just zero, but it's really the zero product property. After that, scooch this over. A is axes. That's actually the plural of axis. Here we're going to determine, there's really two L's. We have local behavior, which is not end behavior, but it's the behavior at the x-intercepts. And the other L word is label. We're going to label the x-intercepts with the number and the behavior. We have a little notation. P, we're going to plot everything. Okay. Plot and label kind of go together, right? And then G is last but not least is to graph. So again, this first example is really so vanilla. I'm sorry. It's so basic, but got to start somewhere. Let's start nice and slow. Now, let's talk about local behavior. That's its own little side conversation, right? What is local behavior? Well, I'm glad you asked. Let's do a little intermission. In a nutshell, We could do a deeper investigation on this, but we're not going to do that right now. The local behavior is going to be determined by multiplicity. You're writing this down, right? Because like, seriously, this is very important. Determined by multiplicity when the polynomial is in factored form, not standard form. When we're in standard form, when we're looking at an exponent, we're looking at what we call the degree of the polynomial, which is the largest exponent of the polynomial when it is in standard form, descending exponential order, combined like terms. And that will tell you end behavior. However, each factor has a multiplicity or an exponent around that factor. And that multiplicity will dictate the local behavior, how the graph behaves at that x-intercept. We're really going to focus on 3 different scenarios visually. And really numbers are infinite, right? There could be infinite multiplicity, but everything even will behave similar to 2 as a multiplicity. And everything odd greater than or equal to 3 will behave kind of like 3, like a cubed. The 1 is the only odd that kind of has like a unique slant to it. So let's look. Say you have your polynomial in factored form. You have, I'm going to just draw it out. Say we have 3 factors. Say one of them has no exponent on the outside. Say this one has a 2 and this one has a 3. All right. Now, if you have nothing out here, you don't really have multiple, right? You just have 1. So I'm just going to call it a multiplicity of 1, even though it kind of doesn't make sense because you don't have multiple. We have 1, but it's fine. So we have a 1, we have a 2, we have a 3. So these are the 3 scenarios or cases of what we're looking at. Now, also when it's in factored form, lots of things can be going on inside of these parentheses. I'm just going to say like it's really x plus something, right? Maybe it's an x minus something. Maybe it's just an x, which is really like x minus 0. So something along these lines you're going to have in your factored form. You also had set them all somewhere along the way equal to 0 to get your x-intercept. So x equals, I'm going to call this x-intercept A. This one is x equals B. And then here x equals C or 0, whatever, okay? We just got these 3 random x-intercepts. Now, if the multiplicity is 1, a 1 for the power on the outside of your factored form means that that x-intercept will behave like a linear equation. So it's a linear local behavior. If that multiplicity is 2, that means that the x-intercept that came from that little thing, it's like a little chick came out of an egg. What kind of egg did it come from? An ostrich egg. It's not a chick, it's an ostrich. It came from a chicken egg, it's a chicken. What egg did it come from? So the egg is the factor, parentheses, what kind did it come from dictates what's going to come out of that egg, what's going to grow from that egg. Is that okay? Does that make sense? So if it's 2, that means the local behavior is going to be that of a quadratic. And last but not least, if it's a 3, that means that that x-intercept, it's going to have the behavior at that x-intercept of a cubic. Now, let's elaborate a smidge more, shall we not? We shall. So linear, okay, linear, quadratic, and cubic. What do those all look like? Well, linear. Here's a little, pretend that's the x-axis. If that's your x-intercept and it's linear, now we're not going to know which of these 2 things it's going to be. It's really on large scale just dictated by the end behavior, which I always start on the right. We'll talk about that in a second. Linear is going to cross through that x-axis. Locally, it'll look like a line. Not looking at the whole picture. We're not looking at literally the big picture. We're looking just right there, like a spotlight on that one spot. So locally, if we just did a little spotlight, it's going to look like a linear cut, like a straight line. Or maybe it's going this way. It all depends on which way are we going, where are we coming from, and where are we going to. So it's going to be pretty straight as we cut through one of those two. It's not both of them, it's one of them at each linear x-intercept, or 0. Quadratic, well, what does a quadratic look like? Glad you asked about that. Here again, a little sample x-axis. We have two possibilities. A quadratic is, hopefully we know, parabola is what we call the graph of a quadratic function. So it's going to kind of look like a little U. It's going to touch and go. So it's either like that or it's like that. So it either has like a bit of a happy face look to it or a bit of a frowny face look to it. And it only touches, boop, at that one spot and bounces right back up over. And now cubic is going to sort of be linear, where it is going to cut through to the other side, except we got a little flavor now. So a cubic, it's going to look like maybe it was a parabola, but it broke its arm and one fell down. A lot of people draw this little curvature the wrong way. Try to mimic what I just did. That's one scenario. And then the other one might look like that. Again, just imagine your arms up. You can't see mine, like kind of like this. And then one falls down. So it's like a half parabola, but one's up, one's down. All of the even will kind of have this look to them. Okay, so all of the even. What really happens is it sort of flattens out the U and it looks a little boxier as that even number gets larger. So it kind of squares off a little bit and it looks like a flatter bottom. And then the cubic, the same thing happens. So this is all odd, but greater than or equal to 3. And as the numbers get bigger, it also will kind of box off. So what do I mean by that? Just to draw a little on the side. And none of this matters. Like, no one's going to make you go crazy with that, but it might square off more like that or more like that. And then same idea for the cubic. It might be a little more squared off, okay? A little stiffer, whereas like a 3 might be a little flatter and stretched out, you know? So in a nutshell, that's what your local behavior is. It is how your graph behaves at the x-intercept locally at one unique spot, and it is determined by the little egg that x-intercept hatched from, and that egg is the factored form. If it was just x where the x-intercept is 0, you might not have parentheses, so we're going to have to figure it out. Spoiler alert, you'll see one like that soon. Right? Ready? Let's go. Getting all the information you need, right? Let's do it. Okay, so now, do I need that? I hope not. You don't have that in front of you. I don't know what to tell you. You should have wrote it down, right? So here's our example. I'll save my little cute graph for a second, a little later, but let's start the steps, which you have in your notes because you're such a good student, right? So here we go. Okay. Step 1, end behavior. Again, I don't know what to tell you. You got to know how to do end behavior. If I have that video, I'll share it. The leading term, LT, is positive x to the third. If it's positive on the right side, it's finishing pointing upward. And then if it has an odd degree, not multiplicity, we call it degree here, then the beginning is the opposite. So we can say the end behavior from left to right, we would describe it as down and up. Okay, end behavior, check. So that's our exotic. Next step, funky. Funky is to factor. So I'm going to factor this, y equals, I'm going to start by taking out a GCF of x. That leaves me with x squared minus 4. I can factor this a bit more because here I have the difference of 2 squares. And remember, you do need to fully factor. So we get conjugates, x plus 2, x minus 2. So exotic, done. Funky, done. Next is the zero product property. That means what we're really doing is you're setting y equal to 0. And essentially what we're doing, I'm putting it on the right, is we're solving a polynomial equation by factoring. So you set each of those factors equal to 0. Hence, this is the zero product property. So what are these factors? We have one here, one here, one here. So I have x equals 0. I have x plus 2 equals 0. As you see, I'm doing my work kind of underneath each factor. I have x minus 2 equals 0. Subtract 2 from both sides and we get x equals negative 2. add 2 to both sides, I get x equals 2. So what are my x-intercepts going to be? I have x-intercepts at 0, -2, and 2. If I really want to be precise and correct about this, this is really 0, 0. This is -2, 0. And this is 2, 0. X equals something is really a vertical line, so it's not really proper to call that an x-intercept, you know? So really it's at a point. And they all, if you think of it, have the last name 0, hence us calling them the zeros. Like think of it as the Smiths, you know, like it's a family and they all have the same last name. Now we have exotic, funky, zebras, avoid. Avoid is axes. Voila, I have my axes ready to go. Little, we're going to label the behavior of each of these, and then we're going to plot and put all that on the graph. So what do I mean by label? We're going to label the local behavior. These all came from 0, -2, and 2. They came from these eggs over here. Eggs. Listen to me talking crazy. First power, and first power. There's no like multiple of anything. Multiplicity, for lack of a better word, is 1. And that didn't even have parentheses. That's okay. We will survive. So that means linear, linear, and linear. They're all linear. So I'm going to go ahead and plot those points and label them on here. I tend to not go too crazy with tick marks. I only label the ones that matter. So I have 2, -2, and really I also have 0. And then I'm going to put little L's, L, L, and L, because those are all going to be linear. Also, while I'm plotting things on putting it on paper, while I'm doing all that, I can also stick on my end behavior arrows, which on the left is down, on the right is up. So down, I'm going to go right there, and up. And you kind of want it to be somewhere where you can naturally come off that point and get to it. So somewhere like that. Big time advice, huge. This is a golden nugget, all right? Think of this as your insurance policy, okay? Like you're buying insurance. If you start drawing your graph of your polynomial on the right, you're insured to avoid big mistakes, because most students, when they do their end behavior, if they're going to get only half of their end behavior right, they're probably getting the right side right, correct? Because we're pretty good at knowing where the graph finishes based on the sign. People tend to mess up where it starts, especially if it's a partially in factored form and all that. Maybe you add up things wrong, incorrectly, and you get odd or even messed up, and then your beginning is wrong. So if you start with the wrong end behavior on the left and draw your whole graph, now everything's wrong. So to avoid that, again, the big time insurance guarantee, protect yourself, is you start with your drawing on the right side, and ideally we would like to meet up with our left side. Okay, so here we're going to draw our graph, and a polynomial is a smooth, continuous graph, no harsh edges. It's curvy and smooth. So we're going to go from our right end, and we're going to work our way to here. And when I get there, I'm planning ahead. I'm not just going to wait till I get there. And I got to decide, am I going to cut straight through like a linear? Am I going to cut through like a cubic? Or am I going to kind of quadratic little bounce? And as we know, we're going to cut through linear. Now, it can't be straight forever. We're going to have to turn around, and you're going to have to cut through this one like linear. There you go. And then again, I can't go up straight forever. I got to turn around because you have to pass through these 3 points. And then here, again, we cut through pretty straight. Okay, I know you might be like, well, that looks like a quadratic. No, this quadratic curve bounce is up there, and it's down here. It's not happening at the 0. And really, that's just the end of the graph. There you go. That's our sketch. It's absolutely beautiful. When we want to figure out the highs and the lows, well, that's what calculus is for. And we'll learn that in calculus, or we'll learn how to do that using different features on a graphing calculator or so. But by hand, we do it in calculus, just not right now. Okay? So that's the end of this example. In our next example, I will be graphing. If I can find it, I can show you now for you. I think I'm graphing this bad boy over here, which will showcase the quadratic as well as the cubic local behavior. And I also have a negative leading term. So little different there. So to see that, click the thumbnail below. If you enjoyed this, or if you love my dog's ducky pajamas, you could give the video a happy thumbs up, right, Dal? Yeah? Dallas says, please subscribe for more lessons. Mom's really annoying. All right, so enjoy. Hope you feel smarter, and I'll see you, or you'll see me in the next video. Bye.